Okay. Hello, everyone. Welcome to this tech talk on accelerating semiconductor IC design using Ansys simulation. I am Vinayakam, and I will be the presenter for this session. I would like to give you a brief intro about myself so that you have the context on the semiconductor simulation topic that I'm about to share with you. I have been working in the electronic design, automation, and semiconductor space for over 15 years. My focus area in this space has been power, noise, and reliability simulations. I love to solve multiphysics challenges that require combining technologies across different domains. In my role, I have worked and collaborated with various semiconductor companies in enabling and deploying advanced simulation workflows for their next generation semiconductor designs. In this tech talk, I would like to share with you my insights on the essential role of simulation for semiconductor IC design. Now, I will turn off my video to sort of save bandwidth, and I will bring up my presentation in full screen. Give me a minute to do that. So I'm just confirming that the presentation is showing. Yes.
Yes, sir.
Okay, thank you. So in this presentation, we'll talk about accelerating semiconductor IC design using Ansys simulation. I have outlined the agenda for this presentation here. In this presentation, we will discuss the trends in the semiconductor industry. As you know, we are moving to advanced technology nodes for power, performance, and area considerations. We will look at what are the needs and challenges based on these semiconductor industry trends, and I will specifically focus on the needs and challenges from a power integrity, power efficiency, and reliability point of views. After that, I will then share the Ansys simulation workflow that can address these particular semiconductor design challenges. I will share with you how the workflow looks like and how you can apply the power of simulation to the semiconductor design workflow to accelerate the development of the semiconductor products. Once we discuss these 3 points, we will conclude and then have a Q&A session. So that would be the overall structure of my presentation. And now let's move on to the first point. I would like to start with standard terminology in semiconductor design. SoC is a frequently used acronym in semiconductor industry, and it stands for System on Chip. An SoC is a chip that integrates several components of the system on the same chip. For example, a smartphone can have various components like camera, Bluetooth, CPU, and these are typically integrated into the same IC. In a general SoC, you will find digital blocks and custom blocks like memories and analog I/O. Now, while designing such an SoC, simulation is extremely essential. Simulation needs to be done before the IC is manufactured. This IC simulation needs to ensure that the chip will work as expected from a power, performance, and area perspective, and it also needs to meet the reliability standards defined by the target market. As you know, Manufacturing a chip is an extremely expensive affair. Companies look for first-time silicon success. So simulation of the semiconductor SoC is extremely essential, and it needs to be done prior to manufacturing the chip. Now let's look at the SoC simulation workflows with Ansys semiconductor products. During the front end of the IC design cycle, the designer creates the RTL description of the design. RTL stands for Register Transfer Logic. During this stage in the front end design, the IC designers use Ansys Power Artist to understand the power consumption of the IC design. Using the results from that simulation, the IC designer will look at improving the design from a power consumption and from power efficiency point of view. I will expand on this in my later slides. After the front end stage of the design, we move to the back-end stage where the IC designer works on the placement and routing of the layout. In this back-end stage, the IC designer uses Ansys RedHawk-SC to understand the power integrity and voltage drop inside the IC during its operation. I will expand on this power integrity topic in great detail in my coming slides. Remember that I mentioned an SoC will have digital and analog blocks. The custom blocks like analogs and memories are simulated at the transistor level using Ansys Totem. Once the entire SoC simulation is completed, this SoC or IC typically goes into a package. At this stage, the simulations are performed on the IC and the package together to ensure that they work reliably together. So I talked about SoC design, and I gave a brief about SoC simulation using Ansys at various stages in the design. Now let us switch gears and look at the evolution of semiconductor design complexity. In the 1980s, most of the design was done by hand, and mostly the design was at a transistor level. In those days, people only needed to check the functionality of the design. As designs progressed into the 90s, we also needed to start looking at checking the timing of the ICs to ensure that the circuit met the timing performance that we expected. As designs progressed into the 2000s, power consumption, power efficiency became an increasing consideration. Scrolling forward to 2010s, more components were integrated into the IC, leading to the system on chip terminology that we talked about earlier. The reliability of the SoCs became an added challenge. Towards 2015 and later, we moved to stacked die structures and sub-100 nanometer technologies, where thermal and EMI considerations became added challenges from a physics simulation point of view. Recently, the industry has moved to advanced FinFET technology nodes like 5 nanometer and 3 nanometer, and the ICs have evolved into complex 3D IC stacked die structures, which can have both horizontal and vertical stacking. So with such complex structures, there is much more added challenges like thermal, EMI, and mechanical simulations and mechanical stress simulation on these structures that need to be done in order to ensure that the complex IC is working as expected to be successful in the market. So in a nutshell, as semiconductor design has evolved in complexity, it becomes more and more important for us to simulate each and every aspect of the physics, like power, reliability, thermal, and mechanical, to ensure that the complex semiconductor IC design that we are building works perfectly as per our expectation. In this slide, I'm showing how semiconductor design and simulation fit together with the example of an airplane analogy. So here, the IC design typically happens through the implementation workflow, and this generally progresses from the RTL stage, then on to synthesis, then on to place and route, and then on to verifying that the layout and the function works fine, and then on to what we call the final tape out, where the chip is sent to the manufacturing. While this design implementation is being done, it is essential to perform IC simulation. And all the Ansys simulation physics are shown in yellow color and are tagged on the wings of the airplane in this diagram. The IC needs to be simulated to ensure power integrity sign-off. It needs to be simulated to ensure that the reliability requirements are met. It needs to be simulated to ensure the EMI, EMC constraints for the target market are successfully addressed. So the reason I use this airplane analogy is to emphasize that without the wings, an airplane cannot fly. Similarly, the IC simulation for various multiphysics is extremely important to ensure the success of a semiconductor IC design. So in this slide, I mentioned various types of simulations that you can see highlighted in yellow. I will specifically focus on power sign-off, which is primarily focused on power integrity and power efficiency. I will focus on power simulations in great detail. I will also touch upon reliability simulations to a brief extent. In the interest of time, I will not go into detail on all the other simulation aspects. If you have questions on those areas, please feel free to reach out to us and we would be happy to help you. Now let's focus on power integrity simulation. In this diagram, you will see a simplistic representation of an IC design. There are power pads and there are standard cell instances inside the IC. There is power grid layout that connects the power pads to the various inverters, buffers, and memories that are situated inside the IC. The connection from the power pad to the instances happens through the power grid layout, and it can contain a lot of RLC impedance parasitics as shown in this figure. Now, I know that most of you may be new to the concept of power integrity or voltage drop. So I wanted to use an analogy with how electricity is transmitted through the electrical grid. So electricity starts from the power plant and it travels through the various transmission lines, transformers, and then it reaches our house. In a similar fashion, inside the IC, the power is transmitted from the power pads all through the power grid layout, including and covering all the various layers in that power grid layout, all the way down to the inverters, flip-flops, or memories that are present in the IC. So when current is traveling through this power grid, the impedance of the power grid caused by the RLC parasitics of the layout geometry will result in voltage drop. This means that the voltage seen at the actual inverter or the flip-flop will be much lower than the voltage that you would see at the power pad of the IC. This voltage drop problem becomes severe as more and more components get fitted onto the system get fitted onto the SoC. In this diagram, you can see an example of a smartphone operation. In the first section, there is only the map application that is running. So during that time, there is a certain amount of power and current that is consumed by the IC, which results in a certain level of voltage drop. Then the person using the smartphone turns on a streaming service, which means there is one more application that is running, which means more power and current are consumed into the IC. Then the person gets a call on a smartphone. So then more power is consumed in order to activate that particular application. And all these applications running together can consume a lot of power and current, which can cause a loss of supply voltage or a drop in the supply voltage. So why is this voltage drop a problem? This is because the power supply noise margin is decreasing significantly, as you can see from the red and the blue curves. The red curve shows the supply trend over the years. Our supply voltage has decreased from the order of, let's say, 1.5 volts, 2 volts, to dramatically down to as low as 0.6 volts or 0.5 volts. On the other hand, the blue curve that shows the power noise impact has significantly increased due to increased power density and increased complexity of the layout parasitics. So both these trends combine to decrease the power supply noise margin, and this becomes a significant impact to a semiconductor IC design. Due to this reduced supply noise margin, it becomes even more important to simulate and ensure that the power integrity and the voltage drop requirements are clearly met during the semiconductor design. Now let's look at a little more detail as to how voltage drop creates risk for the IC design. In this diagram, you will see an example of a simple flop and the VDD and the GND pins. On the left side, there is an example of the blue waveform and the yellow waveform, which show the VDD and the GND voltages for this particular flip-flop. You will notice that with a sharp dip in the VDD voltage and a sharp bounce on the GND pin, the effective supply voltage drops to a very low value, which means that the flip-flop will not even be able to operate, and that can result in a logic failure at the output of the flip-flop. So this can be one type of risk that is impacted, that the design is impacted due to the dynamic voltage drop. Now let's look at the second set of diagrams. Even if the voltage does not result in a logic failure, the voltage drop as shown in the second diagram can significantly impact the transition time and the delay from the input or the clock pin of the flop to the output of the flop. And this can potentially lead to a timing failure, and the chip may not work as expected. Now let's look at the third diagram. Here we see that there is a resonance happening on the power lines, and the voltage waveforms on the power and the ground lines are impacting the clock timing, leading to jitter in the clock tree. This can potentially lead to a clock failure. In order for us to, so these are the different types of risk that voltage drop can induce into your semiconductor design. Now, in order for us to understand voltage drop in detail, we need to understand what are the various causes of voltage drop. So that brings me to my next slide. In this diagram, I'm showing a voltage drop map of the IC. And you can see that on the lower right, there is a high drop area. And this high drop area can be caused due to many different factors. For example, That high drop area could have a cluster of high power cells that are all sitting together, driving a high load and firing at the same time. This can cause a high amount of simultaneous switching and power consumption, which can cause a high voltage drop in that region. There could be other reasons as well. It could be that the high drop area is situated in a part of the IC layout where the bump and the RDL layer are poorly designed or very weakly connected. Or it could be entirely an issue with the package layer routing, where the number of package layers are probably insufficient and the routing is so congested that the fragmented routing leads to high inductance in that particular area, which in turn causes high LDI by dt, which in turn results in a high dynamic voltage drop in that particular area. As we can see from this slide, the voltage drop issues are varied in nature and they can happen due to a multitude of reasons. Now, in this slide, I want to talk about the key trends, especially in the recent technology nodes like 7 nanometer and 5 nanometer, and what are the key trends that contribute to dynamic voltage drop. We have represented this challenge here in a very simple manner with 3 diagrams. So let's look at each diagram in detail. The first aspect is the increase in simultaneous switching noise. This is caused by the industry trend of packing more and more transistors into the same area or size. The graph shows the transistor density trend from 28 nanometer to 16 nanometer and then to 7 nanometer based on a published source. As you can see, the transistor density increases significantly as we move from 16 nanometer to 7 nanometer and below. The second aspect is the power delivery network, or PDN as it is called. Power grid complexity has significantly increased from 16 nanometer to 7 nanometer. As this diagram shows, power grids have become so dense and complex that we now see the PDN to have as many as 10 billion plus nodes. These two factors, SSN and PDN complexity, lead to a significant challenge in dynamic voltage drop, or DVD. From a voltage variability perspective, this voltage variation happens over time, as shown in this waveform, and the voltage variation happens in different regions of the chip, as shown in this heat map. Now let's look at how these dynamic voltage drop trends impact the timing of the instances and the clock network. Again, I have represented the challenge here in a very simple manner with 3 diagrams. Let's look at each diagram in detail. The first diagram shows the supply voltage trend. As we move to advanced technology nodes, we are reducing the supply voltage on our designs. As you may remember from our CMOS basics, power is proportional to the square of the supply voltage. So lowering the supply voltage yields significant power savings. Over the last few years, the industry has moved from supply voltages in the range of 1.8 volts or 2 volts towards 1 volt or lower for 7 nanometer nodes. We also see a trend of moving to near threshold supply voltage operation, which means the supply voltage can be as low as 0.5 volt. Now at such ultra low voltages, the timing and delay behavior of the transistors can have significant variation. The margins become razor thin, so it is very important that we accurately account for voltage variability. These two aspects, ultra low voltage operation and cell delay variation, contribute to create a voltage drop on timing challenge. This means that silicon performance may be affected for such designs. So margin-based approach, where we just assume a threshold for voltage analysis and a separate threshold for timing, such a margin-based approach will no longer be scalable. So in the previous slides, we looked at semiconductor trends. We looked at the power integrity challenges. Now, let's look at this from a big data platform point of view. So why am I talking about big data here? The reason is that semiconductor designs have grown in complexity over the years. In my earlier slide, you saw that semiconductor designs now have a variety of operations integrated into the SoC. And even the chip is now becoming much more complicated with the migration to 3D IC structures. This now means that modern semiconductor designs have hundreds of millions of instances. And each of these instances have their own layout, physical properties, like the layout, wire, and the pin geometries. They have their own electrical properties, like the voltage information, the power information, the current waveforms, and the timing and the logic waveforms for each pin inside these millions of instances. So the amount of data that we store for this kind of a semiconductor simulation can easily range in the terabytes or upwards range. So this means that we need a big data platform to handle the complexity of semiconductor design simulations. So that is why in this slide, I'm talking about the big data platform for semiconductors, and I'm showing you the Ansys SeaScape platform here. So this is industry's purpose-built big data platform for semiconductor simulations. The platform has its own infrastructure, its own database, various APIs to query the database, and a graphical UI for the user to visualize the results. This platform is available to the user in the Python shell, and the distributed data compute from the platform enables the user to do complex data analytics and machine learning directly on the SeaScape platform. In order to perform semiconductor simulation, we need various engines as well. So these engines are integrated into the SeaScape platform. For example, we need a power calculation engine to calculate the power consumption of the design. We need a geometry processing engine to process the layout geometries for wires, pins, vias, etc. We need an extraction engine that converts the geometries into the RLCK parasitics. And then we need a metric solver engine that takes in that RLCK and is able to do a metric solve operation. All these engines also interact with industry standard formats like Liberty, like layout exchange format or LEF, or design exchange format or DEF, so that any semiconductor design can be imported into this platform and enabled for semiconductor simulations. Now let's look at the advantages of using SeaScape platform. This is a big data platform that naturally enables us to scale and handle massive full chip designs with billions of instances. One of the key differentiating features of the SeaScape platform is elastic compute, which allows you to elastically distribute the semiconductor simulation into hundreds of cores, allowing you to get an efficient use of hardware resources. The platform also provides powerful multivariable analytics. The user has a lot of flexibility in the way to open multiple databases, multiple views, and do quick analysis and reviews. The layout GUI is so fast that it can load a multi-billion design instance in seconds, and the user can do quick interactive debug. From a usability point of view, there is MapReduce Wizard and a console built in, so that the user can get online built-in help as quickly as possible. So I talked about semiconductor design challenges, power integrity trends specifically. So now I want to talk about RedHawk-SC, which is Ansys simulation product for power integrity sign-off. So this is built on the Ansys SeaScape platform, and RedHawk-SC reads in the layout geometries. It converts the layout geometries using the extraction engine into RLCK circuit, which is then solved using the metric solver engine. The user can perform a variety of distributed data analytics using the elastic compute feature and visualize the result in various forms. All this can be done directly in the RedHawk-SC environment. I talked about voltage drop. So here's a circuit level representation of what voltage drop means. So from the power pads, there is the power grid geometries, which are extracted by the tool, and they get converted into R, L, and C networks. The instances consume current, which are both time varying and voltage varying. There can be decaps, decoupling capacitors that are intentionally placed on the IC layout, which have their equivalent ESR and ESC values. There can be other instances that provide intrinsic capacitance. All these are connected together in the circuit, and then the metric solver is done for all these millions of instances together. And the voltage waveform at each and every power pin and each and every ground pin of the instance is computed. So all this happens in the RedHawk-SC simulation environment. And once that is done, the user has a variety of options to visualize the results. In the center, I'm showing what we call a dynamic voltage drop heat map. So here, all the instances inside the IC are represented with a color range for their voltage drop. So all the 100 million instances can be directly seen on this voltage drop heat map. Another way to visualize this is to use a voltage drop histogram. And a third way that I've shown here on the left is to look at each instance in detail. So you should be able to see the voltage waveform, the current waveform, and the logic waveform for a particular flip-flop instance that is presented inside your IC. So this is an extensive amount of big data results and analytics that you can perform and visualize from the SeaScape environment. Now I want to talk about where in the design flow this can be applied to ensure that power integrity challenges are successfully addressed in your design cycle. So during the start of the design flow, there is the power planning stage where you want to identify and fix issues very early. This can be done by using RedHawk-SC to do early grid quality checks. Then during the block level analysis and sign-off stage, static and dynamic voltage drop analysis and power and signal electromigration analysis can be done at the block level to ensure that all the local effects at the block level are successfully addressed. Once the block level analysis is closed, all the blocks are then integrated into the full chip or the SoC, and a full chip static dynamic voltage drop analysis and an electromigration analysis is done to ensure full chip analysis is successfully converged and closed. Once the full chip analysis is complete and the various issues are identified and fixed, a chip power model can be generated and handed off to the package or system level guy to do a system level analysis combining the die model and the package layout. So we talked about semiconductor trends and power integrity challenges and how Ansys RedHawk-SC helps enable simulation to overcome these simulation challenges. Now, I want to switch gears and I want to talk about power efficiency simulation. In this slide, I'm showing a variety of target markets that the semiconductor chips go into. For example, on the mobile market, battery and thermal are key considerations. While holding a mobile phone, you don't want too much heating on the smartphone, and you also want the smartphone product to have a long battery life. Both of these criteria, battery and the thermal aspects, ultimately boil down to power consumption of the device. So it is extremely important that while a semiconductor IC for a mobile is designed, there is conscious thought in terms of simulating and trying to optimize the power consumption of that particular design. The same holds true for a variety of semiconductor markets. For example, in the IoT market, battery life is extremely important. So the lower the power consumption of the IoT chip, the higher the battery life and the greater the market success for that particular design. From a power efficiency point of view, most of the power savings and the power decisions have to happen at the early stage of the design cycle. Most of the power savings as shown in this graph happen from the architecture stage all the way to the synthesis stage. Beyond the synthesis stage, once the gate level data is designed and generated, the potential power savings are extremely low. So it is very important that during the front end stage of the semiconductor design, the designer spends a lot of time into identifying all the potential power savings that can be done during the RTL design phase prior to synthesis. So this enables the designer to optimize the power and make early design trade-offs. Here's an example that shows why this is important from a turnaround time perspective. Using the RTL design and using power feedback from the RTL level is very quick. It's just 22 minutes. Whereas if you rely on the gate level design and then the power calculation, the turnaround time is too huge to meet your time to market considerations. Another aspect is that at the front end stage, when you're doing RTL power, you can visualize, analyze, and debug power from a function point of view, instead of at a gate level where the power is just a per gate thing and you just see a sea of gates. In this slide, I want to summarize from a power efficiency point of view, what are the 8 best practices that we see semiconductor designers doing? The first aspect is to do architectural trade-offs to ensure that you can get what is the best architecture to optimize your power consumption. The second best practice is to audit your design for power efficiency. For example, are there redundant clock gates in your design? Are there constant clock enables in your design? All this can be audited and fixed to optimize the power for your design. The third step is to profile real application scenarios. If you look at any smartphone, it can have a variety of use cases. So it's very important to profile those real application scenarios and look at the power consumption. In this particular example diagram that is shown here, we see a very simple transmit mode and a receive mode. But you will notice that there is a residual receive activity in the transmit mode, which should not have been there. So that's a bug in the design from a power consumption perspective. And we can identify this and fix this using Ansys Power Artist. The fourth best practice is to always budget your power. So look at what is the peak power and what is the average power for your design, for your various operating modes, simulate them with PowerArtist, get the power numbers, and then cross-check those against your budget. If you find that your powers are exceeding your budget, you can use the PowerArtist schematic GUI to debug the power, drill down to the details, and identify where the power hotspots are coming from. Once you debug that, you can then look at how to reduce the power consumption. Once you identify the power reduction opportunities and make fixes, you then rerun PowerArtist, ensure that the power now meets your budget. But remember, all this is not just at the final phase of the RTL design. This needs to be done day in and day out throughout your entire front-end design cycle. So this is what we call the RTL power regression flow. So every day or every week in your milestone, you check all the power efficiency metrics. This enables you to clearly track what changes in your RTL design led to changes in the power consumption and take proactive action to go and fix and optimize your design. Now, once you have optimized your power, you have closed the RTL block, you can create a power model and then hand it off to gate level or system level for advanced simulations by using a good power model for your representative RTL block. So this provides a high-level overview and summary of the power efficiency simulation and the related best practices that we see in the semiconductor design space. I next want to touch upon the reliability simulation aspect. The electronics industry is the electronics industry from a reliability point of view is undergoing a phenomenal challenge to meet the demands of the semiconductor market and its applications. So this comes in the form of increased safety requirements in the automotive market. There is increased connectivity requirements in the 5G market. There is increased performance considerations in the high performance computing and the data center market. And there is power efficiency and complex integration needs in the mobile market. These trends continue to require the migration to advanced technology nodes like 7 nanometer and 5 nanometer, and the usage of FinFET style transistors instead of the planar style transistors. So all these application trends continue to push the requirements in chip package system reliability aspects that range from electromigration or EM, thermal impact of on the IC and the system, and also on electrostatic discharge in the system. Now, if you look at the reliability level today, it is increasing as the devices migrate from being a standalone device and then into a connected device, which then evolves into a cooperative system on demand, as in the cloud era, and to finally into an autonomous collaborative system like in ADAS or an autonomous vehicle. Looking at the chip failure impact, we can see that in a standalone device, it's mostly inconvenient. In a connected device, it can become annoying, but it becomes dangerous in a cooperative system, and it becomes lethal in the latest autonomous systems where safety and reliability become paramount. Now let's look at the diagram on the right side, which is popularly known as the reliability bathtub curve. This shows three types of failures: early failures, random failures, and wear out failures. Due to the increase in power density and the electric field intensity in advanced semiconductor designs, we see that the wear out failures category, especially the category in the wear out failure, has an increase in failure rate. This means that the bathtub curve continues to shrink further, and maintaining IC reliability is becoming a very critical challenge. So designing for reliability is a must-have in the advanced semiconductor designs, especially in the FinFET era. Now let's look at how Ansys multiphysics platforms can address these reliability challenges in advanced semiconductor designs. The IC designer can use Ansys Totem to perform analog and mixed signal reliability simulation. So these can range from the analysis of power and signal electromigration, looking at self-heat analysis, looking at thermal aware electromigration, and looking at statistical EM budgeting. At the SoC level, you can use Ansys RedHawk-SC to perform the reliability simulations at the SoC level. For chip package reliability, the designer can use Ansys chip package analysis. For thermal reliability, the designer performs a system-level thermal simulation in the ISPAC environment. All the complex designs that we talked about and the move to stack die structures can cause mechanical stress in the design, and this becomes an increasing challenge in the reliability space. So they need to be simulated using Ansys Mechanical to ensure that the structural stress is identified and fixed, and that the structure is reliable for operation. And finally, for ESD, which is electrostatic discharge, the IC designer uses Ansys Pathfinder to perform resistance and current density checks to ensure that the ESD devices are operating reliably well in that particular semiconductor design. Ladies and gentlemen, that is the end of my presentation today. To sum up, these are the main points that we covered in the session. We discussed the semiconductor industry trends that create challenges in power integrity, in power efficiency, and in reliability sign-off. We discussed how Ansys simulation can address these challenges to accelerate semiconductor IC design. We discussed how these simulations can be deployed in design workflows to ensure that the next generation SoCs can meet the power performance area as designed. Thank you for your attention. And now let's look at the Q&A. So there are a couple of questions, but those questions are more detailed. So I will reach out to the relevant person separately offline with details. For people who are interested in the simulation capabilities on the semiconductor space, please do reach out to us. We are available on the website at ansys.com, and it has a specific contact us section through which you can reach out to us. I hope today's session was very informative for you. I did look at the set of questions. So I think those questions we will answer separately offline. So I hope the presentation was informative for all of you. Thank you for your attention, and we can conclude the session now. Thank you.